Hi guys, I just recorded this whole lesson and then it didn't save and I am outraged. So I'm going to do it again and I'm going to do it even better this time. So lucky you. So what you can do, sorry, this is lesson CA6 in your notes package. So there's actually a page ahead of CA6 called Properties of Ionic and Molecular Compounds. It looks like this. Um, I'm not going to go through it. I went through it before and then I realized that the lesson really talks about it, but you can have a quick read over it, probably actually after we have done both CA6 and CA7 would probably be helpful. So just kind of reserve that page for properties of ionic and molecular compounds. So let's go back to this. Oh my goodness, I'm so sad. What a waste. So CA6 in your notes package, please have your periodic table out as well. So binary ionic compounds. So when we're talking about, actually we'll do the recall part and then we'll chat about it. So in CA5, metallic atoms, so that's things below the staircase, like to give up electrons to other atoms to form cations. Again, cations are those positive charges. Non-metallic atoms like to gain electrons from other atoms to form anions. So anions are those negative charges. Again, that lesson CA5 is really important for understanding the next part. So make sure if you didn't watch my lesson, you go back and have a peek right now. So non-metallic atoms may share electrons with other atoms. So non-metallic, again, those are the things above the staircase. And they may share electrons. So where they're not actually transferring and giving up, but they're both kind of holding on to electrons. So we'll talk about that when we talk about molecular compounds in the next lesson. So we're really going to focus on ionic compounds today. So in order to form ions, the elements must gain or lose one or more valence electron from or to each other. So that's just saying transfer of electrons. Oh, transfer of electrons. And again, the compounds that form as a result of this transfer of electrons are called ionic compounds. So today we're going to be talking about binary ionic compounds. We'll do two other ionic compound things in the next couple of days. So binary ionic compounds, when we're talking about something bi, we're talking about two. So we're talking about ionic compounds that have just two elements within them. So a binary ionic compound will consist of a metal, again, forming a cation, and a non-metal, which is forming an anion. Metals are below your staircase, non-metals are above the staircase. So the bond that forms is an ionic bond, which is a bond that involves electron transfer and is a force of attraction between positive and negative charges. Again, when that electron transfer occurs, those positive and negative charges are what actually hold these compounds together. And we'll look at kind of an example of that. So metals transfer one or more valence electrons to non-metal atoms to form cations. Well, the nonmetals gain these electrons to form anions. So we are going to look at lithium and fluorine. So if you want quickly, I'm gonna correct myself right away there. When we are writing things, we're going to be very specific about some rules of naming or some rules of nomenclature. So there is an organization and kind of a governing body of science, we'll call it. It's called the International Union of Pure and Applied Chemistry. It's usually shortened to IUPAC, IUPAC, again, International Union of Pure and Applied Chemistry. And there is a very specific naming system that's used for chemicals, and that allows scientists and chemists and people in medical fields and all over the place that are working with these chemicals to communicate exactly what they are dealing with. And so that's saying if I ship a chemical from our cabinets out to Germany, they're going to know exactly what it is because we speak in the same language in terms of chemistry. So we're going to follow IUPAC nomenclature, and there are specific rules, and I am going to be picky and specific about it. So things like capital letters is going to be something that I'm going to be specific about. So if you saw, I wrote lithium with a capital and then I changed it. So please make sure you do not capitalize things and you spell things right. A good example is always fluorine. It's spelled different than you want it to be. So quickly draw your Bohr diagrams for lithium and fluorine for me. You might need to pause it because I'm not going to wait very long. So lithium in the periodic table, it's atomic number 3. Oh, it has 4 neutrons. That looked messy. So when we're talking about an atom of something, again, we know that we are going to have our number of protons equal to our number of electrons, so representing 3 electrons there. Fluorine, 9 protons, 10 neutrons. Whoa, that was magical. Whoa, and it messed up this. Don't worry guys, my smartboard's still haunted even when you're not here. So again, an atom of fluorine, we want to represent the same number of protons as electrons. Some of you might need to look back at Bohr diagrams so you're putting electrons in the right spots. They are not evenly spaced when we're drawing a Bohr diagram. So 9 electrons represented there in the in both shells, 7 in that valence shell. And so we know that things want to be most stable with a full valence shell. So right now, lithium has 1 valence electron and it has room for 8. So it's going to be easier to get rid of 1 than find 7 more. And fluorine has a spot for 1. So very conveniently, lithium will, I'm using the red marker, that's the problem, transfer that electron to fluorine. And so what we'll end up with as that electron transfer occurs is we will end up with a lithium ion. And we will end up with the ion of, sorry, I made a mistake here. You're going to have to go back. Oh no, fluorine. We're good. I'm not making mistakes today. So the ion that's associated with fluorine is fluoride. I talked about this in the monoatomic ions lesson as well. So we name our cation just as the element name and the word ion. We name our anion as the ending change to IDE as it is in the periodic table. So now if we draw the lithium ion, it is going to have the same nucleus. I gotta keep doing that. There we go. And the ion from fluorine, which is fluoride, same nucleus. Geez Louise, come back up. You guys missed in my last recording. Alana came in and interrupted my lesson, just like old times, because she was here as well. Whoa. I'm at school right now. It's quiet. It's weird. They washed my floor. It's weird. So when we form the ion, again, we want to represent the charges. So lithium now has that positive charge, square brackets around. My fluoride ion has a negative charge. And so what's actually holding this together is that positive and negative charge. Those are attracted to each other. So that's what's actually going to hold an ionic compound together, is those positive and negative charges. They're going to hold everything together. So it says the result is a cation, which is positive, and an anion, which is negative. So the result of electron transfer, which attract each other very strongly due to their opposite charges. Therefore, ionic bonds are strong. So that's important there. So ionic compounds are overall are neutral compounds. So overall, they have no charge. Within a formula unit, there's charges associated with it, but overall it has a neutral charge. So for the example that we just did there, lithium had a 1 positive charge, fluorine had a 1 negative charge. If you have 1 positive and 1 negative, that's going to be equal to 0. So overall it's a neutral compound. I'm trying to drink coffee and I know my microphone's right by my mouth, so that probably sounds gross. So ions in an ionic compound arrange themselves in a regular repeating pattern called a crystal lattice. So they don't actually form just as like 1 lithium and 1 fluorine together. They form a structure that looks like this. So where we would have that fluoride ion, it would be connected to lots of those lithium ions. So that negative anion connected to a whole bunch of that cation. And then any of those cations, if you look, they're connected to some of those anions. And then if you look at one of those anions, they're connected to cations. So it forms this lattice structure. Somewhat important, but doesn't really matter. We'll just be talking about formula units though, which I guess I should explain. So ionic compounds form formula units. Not molecules. So we just try not to use the word molecules when we're talking about ionic compounds, because those should be reserved for molecular compounds. I sometimes will kind of trip up over that, but we should be calling them formula units. So that's a formula unit of lithium fluoride. Ionic compounds are usually solid. And at room temperature. I'm going to add another one here. Ionic compounds. Conduct electricity. When dissolved in water. And so that's what we call, when something is dissolved in water, we call that an aqueous solution. So conducting electricity, what that means is if I take something that's an ionic compound and dissolve it in pure water, so distilled water, not water that's coming out of your tap, that's not pure water as much as you would like to think it is, but distilled water where everything in it is that H2O molecule. And I'm allowed to use molecule there. If we dissolve something like sodium chloride, which is table salt, which is what you put on your French fries, if we put that into water, it would actually, if we ran electricity through it, it would conduct electricity. I have these little conductivity meters that usually I do some little demos of that, but I might try to post a video of conductivity. If I took something like sucrose, which is like white sugar, and put it into dissolved it in distilled water, and use my conductivity meter, it actually doesn't conduct electricity because our molecular compounds don't form those ions. So there's no electron transfer, therefore it cannot conduct electricity. So naming, nomenclature, again, I'm going to be sticky with the rules, so make sure you are following them. So the way that we name it, so our cation or our metal is named and written first, and the anion is written second with the IDE ending. So when we name the cation part for the step one, we keep its full name. So don't go trying to change magnesium to magnesite or something like that. You keep the full name. The anion, though, again, it's going to have that IDE ending, which it's in your periodic table underneath each thing. So if you look at atomic number 9, fluorine, if you look at the very bottom of its box, it says fluoride. Because some of them aren't just changed at the ending, they mostly are, but fluorine is changed to fluoride. Oxygen is not oxygenide, it's just oxide. So some of those ones that are a little bit confusing, just look in your periodic table for how to change the ending to IDE for your nonmetals. Again, let's put a big star, no capitals. Pay attention to your spelling. Um, Point 3 here doesn't really make sense. Oh, no, it does. Sorry, this is not the one. It says, do not use prefixes when naming ionic compounds. Subscripts do not affect the name. So that's saying we ignore numbers in this case. So I'll show you what that means with one of these. So again, following these steps for a couple of the naming ones. So the first one, name your cation first. So looking in the periodic table, we have sodium, and we have chlorine. So sodium is the metal, so we name that first, our cation. And then we name, second step is anion is second with the IDE ending. There is a space in between those, so don't try to mash it in as one word. So sodium chloride. It's not sodium chlorine, it's sodium chloride. Next one, CAS, so looking, Ca is our metal. It is calcium. S is our nonmetal, sulfur. So we will name this calcium, but we'll spell it right. Calcium sulfide. Next one, so you'll notice that in these formula units or in our formula, it looks like it's always the metal is the first letter or letters, and then your nonmetal is the second, and that's how it should be. So the next one, lithium bromide. And the last one here, so our metal is magnesium. I don't know why my smartboard's being even more haunted than usual. So magnesium fluoride, Fluoride. So this last one is the one that kind of applies to that point 3 up above. It says, do not use prefixes when naming. Subscripts do not affect the name. So that's this little 2 that's there. That's called a subscript. So if you're working in a Word document, you can subscript things down where you make the numbers little and lower. So that's a subscript. And they don't affect the name. They're important, but we don't need to worry about them for the naming. So where they're important is when we're writing the formulas for the ionic compounds. So it says determine if the compound is molecular or ionic. So again, we know if it's molecular, or we know if it's ionic, if it has a metal and a nonmetal. That's how we can tell when it's an ionic compound. It says if the compound's ionic, determine the charge of each ion. write the symbol and charge for each ion. And then we balance the charges by changing the amount of each ion by adding subscripts. So finding the least common multiple and, if necessary, reduce to the lowest whole number ratio. And so that 0.4, just if you've made a little bit of a mistake, you might come to that and you just need to reduce it. It's like reducing a fraction, basically. So we have the name now. We have aluminum chloride. It's spelt wrong. Put an I in there. Aluminum chloride is an ionic compound because, again, aluminum is a metal, chlorine is a nonmetal. So we know we're dealing with an ionic compound. So looking in the periodic table, looking at aluminum, and it's in group 13 there, it actually forms a 3 positive charge as an ion. Chlorine forms a 1 negative charge. So what we need to do, it says, so this is part 3 or up above there. So it says balance charges by changing the amount of each ion by adding subscripts. So what that actually means is, if we look at those two things right now, Al3 plus, chlorine 1 minus, we can't change these charges. These charges are stuck. They're based on filling those valence shells properly. But what we can do is we can add more of something. So right now I have too many positive charges. I can't change that to Al1 plus, that's not a thing. But what I can do is I can add some more chlorines. So now I have 3 positive charges, 2 negative charges. Let's add another chlorine. So now I have 3 positive charges and I have 3 negative charges. Oh my gosh, I hate this smartboard. So what I actually needed is I needed 1 times that 3 positive charge, and I actually needed 3 times that 1 negative charge to get a total charge of 3 positive. And to get a total charge of 3 negative, you want this number to be the same. You want to have your charges balanced, the same number of positive charges as negative charges. So overall now we'll have a balanced charge. And so we need to think about this part here. We need to think about, I needed 1 aluminum and I needed 3 chlorine. So I'm writing those as subscripts. So little numbers, a little bit lower, not big numbers. We'll see when big numbers come into it. But you don't actually need to write that little 1 that's there. It's really redundant and it can make it wildly confusing. So don't actually write a 1 in if you only needed 1 of a substance. We always assume that there's 1 of something if we've written it there. We don't actually need to reduce it as well because you can't reduce 1 and 3 anymore. So our final formula will be AlCl3. Again, we took out that 1 because it's redundant and it actually can get really confusing later. So we don't write a 1 there if you only need 1 of a particular element. So AlCl3 is our final formula for aluminum chloride. So we see that the subscripts are important because they actually balance out our charges, but when we're naming it, we don't pay attention to the numbers in ionic compounds. Magnesium phosphide. So again, looking at what we have, magnesium, oh my gosh, magnesium forms a 2 plus charge, and phosphorus forms a 3 minus charge. So when I'm writing the charges, those are actually superscripted. So they're supposed to be little and up. So just don't start confusing that. So we use subscripts to tell the relative numbers. We use superscripts for the charges. So thinking about what we need. So right now we have too many, I'm going to shift this down. I have too many negative charges. So I'm going to add another positive charge. Now I have 4 positive charges. So I'm losing it, guys. So I'm going to add another P3 negative. Now I have too many negative charges. Now I'll add another positive charge. So now I have 6 positive charges in total, so 2, 4, 6, and 6 negative charges in total, so 3 and 3 is 6. So writing our formula, we needed 3 magnesiums, 1, 2, 3, and we needed 2 phosphorus. So Mg3P2 is our chemical formula for magnesium phosphide. So the next one is lithium oxide. So again, lithium, oxygen forms a 2 minus. So right now my charges are not balanced. It can balance with a 1-to-1 sometimes, but in this case it definitely does not. So we're going to add another lithium with a 1 positive. And so that will balance our charges. 2 positives, 2 negatives. So our formula will be Li2O. Again, don't write a 1 next to the oxygen. That's just assumed if you have written it that there is one of them. Aluminum sulfide, Al3 plus. Sulfur is a 2 minus. And so adding more negative charges. Now I have 4 negative charges. Adding another positive charge. Now I have 6 positive charges. Adding more negative. Now I have 6 and 6. So my chemical formula, Al2S3. I guess I should put boxes around that. You guys like when I put boxes around stuff, right? You're not here to tell me otherwise. So the stuff on the next page I actually don't really love, but some of you guys really respond to little tricks and stuff that you can do. So another way to kind of figure out the subscripts is just called cross and drop. So when magnesium has a 2 plus charge, oh my gosh, and chlorine has a 1 minus charge, what you can do is switch those numbers as the subscripts. So, oh my gosh, Mg1, I'm not going to write the 1 though, right? So I'm taking the 1 charge from chlorine and writing a 1 next to it, and then Cl2. The 2 charge that was next to the magnesium, I'm sliding it over next to the chlorine. So I actually don't usually love that. You should be able to analyze it in your head. Where it can kind of create a problem is something like this calcium oxide. So Ca forms a 2 plus, oxygen forms a 2 minus. So if you did the cross and drop, what you might accidentally do is say, okay, I'm going to take the 2 from the oxygen, put it next to the calcium, and I'm going to take the 2 from the calcium and put it next to the oxygen. So Ca2O2, but that's actually not in its most reduced form. If you look at it at this point, the charges are actually balanced there with a 1-to-1 ratio. So you should actually balance it as Ca with that little invisible 1, O with an invisible 1. So that's where the cross and drop gets a little confusing. I don't really like it, but it's in the notes, so it's there. All right, here's hoping that this one actually works and saves properly. Peek on to the next lesson, which is Ca7 molecular compounds, once you've done the worksheet for Ca6.